विद्यार्थियों मोशन बारे आज दी इस क्लास विच तुहाडा स्वागत है। In our previous classes we described the representation of a motion on distance time graph or a position time graph as well as the speed time graph or a velocity time graph। ਅੱਜ ਦੀ ਇਸ ਕਲਾਸ ਵਿੱਚ ਅਸੀਂ ਵੈਲੋਸਿਟੀ ਟਾਈਮ ਗ੍ਰਾਫ ਦੀ ਸਹਾਇਤਾ ਨਾਲ ਕਿਸੇ ਆਬਜੈਕਟ ਜੋ ਕਿ ਕਾਂਸਟੈਂਟ ਐਕਸਲਰੇਸ਼ਨ ਦੇ ਨਾਲ ਚੱਲ ਰਿਹਾ ਹੈ ਦੇ ਮੋਸ਼ਨ ਨੂੰ ਡਿਸਕ੍ਰਾਈਬ ਕਰਦੀਆਂ ਇਕੁਏਸ਼ਨਸ ਡਿਰਾਈਵ ਕਰਾਂਗੇ। ਅਸੀਂ ਆਪਣੀਆਂ ਪਹਿਲੀਆਂ ਕਲਾਸਾਂ ਵਿੱਚ ਪੋਜੀਸ਼ਨ ਟਾਈਮ ਗ੍ਰਾਫਸ ਬਾਰੇ ਪੜ੍ਹਿਆ ਹੈ। ਹੁਣ ਅਗਲਾ ਕਦਮ ਇਕੁਏਸ਼ਨਸ ਆਫ ਮੋਸ਼ਨ ਨੂੰ ਡਿਰਾਈਵ ਕਰਨ ਦਾ ਹੈ। ਇਹਨਾਂ ਇਕੁਏਸ਼ਨਸ ਦੀ ਵਰਤੋਂ ਸਾਡੇ ਹਰ ਰੋਜ਼ ਦੇ ਫਿਨੋਮੇਨਾ ਦੀ ਵਾਈਡ ਰੇਂਜ ਨੂੰ ਡਿਸਕ੍ਰਾਈਬ ਕਰਨ ਲਈ ਕੀਤੀ ਜਾ ਸਕਦੀ ਹੈ। A very common and simplest type of one-dimensional motion occurs when the acceleration is uniform. For example, in an idealized world with no air resistance, falling bodies have constant acceleration. When the acceleration is constant, the average acceleration is equal to instantaneous acceleration and the velocity increase or decrease at the same time rate throughout the motion. Today, we will derive the equations describing the motion of a particle moving with constant acceleration. These equations are commonly known as equations of motion. Do you remember a position time graph for a uniformly accelerated motion? If we draw the position time graph for the object in uniformly accelerated motion, it will be as shown here. It shows a curve. Its slope is variable. This graph shows that the object is under non-uniform motion and moving with constant acceleration as the slope of the curve is also constant. If we draw the velocity time graph for the object in uniformly accelerated motion, it will be as shown here. It is to be noted that in the velocity time graph, velocity at time t equal to 0 shows the initial velocity of the object, whereas velocity at any instant tells the instantaneous velocity of the object and the slope of the curve between any 2 points gives us the average acceleration during that interval. Since we have a straight line velocity time graph, that is, velocity varies linearly with time. Therefore, acceleration is constant.
In this velocity time graph, Vi is the initial velocity of the object at time ti and Vf is the final velocity at time tf, whereas the slope of the Vt graph between time ti and tf is equal to the acceleration a of the motion. We know that the slope of a line is equal to the tangent of the line. Here acceleration a is equal to tan theta, where theta is the angle subtended by the Vt line with the time axis, which is equal to the ratio of CD and BD. That is the ratio of Vf minus Vi divided by Tf minus Ti. In other words, Vf minus Vi is equal to A times Tf minus Ti, or we can rewrite the equation as Vf equal to Vi plus A times Tf minus Ti. This is an expression for velocity as a function of time and known as the velocity-time relation for a uniform accelerated motion. Here, initial and final time may be arbitrary. For convenience, let u is the initial velocity at time t equal to 0 and v is the final velocity at time t. Then acceleration a is equal to tan theta, which is equal to ratio of CB and AB. That is the ratio of V minus U divided by T. In other words, V minus U is equal to A times T, or we can rewrite the equation as V equal to U plus A times T.
This is the general expression for velocity as a function of time and helps us to determine the velocity at any time if initial velocity, acceleration and elapsed time are known. To show how it helps, let us try a numerical problem based on this relation. Let a car initially moving with a speed of 2 meter per second and on application of brakes, it comes to rest in 4 seconds. Consider the acceleration is uniform. Then draw the velocity time graph for the motion of the car and measure the acceleration of the car. Here, initial velocity of the car is 2 meter per second and after 4 seconds, final velocity becomes 0. Since the motion is a uniform acceleration motion, hence the velocity time graph of the motion should be a straight line graph. For the measurement of acceleration, we have to measure the slope or tangent of the graph, which is the ratio of BC and AC. Therefore, acceleration A is equal to 0 minus 2 upon 4 minus 0, which gives A equal to minus 0.5 meter per second square. Next is how far the particle moves in a given time if its acceleration is uniform. To describe this, we have to use another property of velocity time graph, that is the area enclosed by the velocity time curve and the time axis gives us the distance travelled by the object.
In this velocity time graphs, distance travelled during the time interval Ti to Tf is equal to the area enclosed by the Vt curve and the time axis during the time interval from Ti to Tf. Therefore, the distance travelled is equal to the area of trapezium BC C dash B dash, which is equal to half sum of parallel side multiplied by the shortest distance between the two sides. Therefore, the shaded area is equal to half of the sum of BB dash and CC dash multiplied by B dash C dash. It is clear from the graph that BB dash is equal to VI, CC dash is equal to VF and B dash C dash is equal to TF minus TI. Therefore, area enclosed is equal to half of the sum of VI and VF, which is multiplied by TF minus TI. On substituting the value of Vf from the velocity time relation, the area enclosed or the change in position becomes equal to xf minus xi equal to the sum of Vi Vi and A into Tf minus Ti, and whole is multiplied by half of Tf minus Ti, which is further equal to the sum of Vi into Tf minus Ti plus half of A into the square of Tf minus Ti. Or, in other words, the relation for final position becomes xf equal to xi plus vi into tf minus ti plus half of a into the square of tf minus ti. This is an expression for position as a function of time and known as the position-time relation for a uniform accelerated motion. This function helps us to determine the position at any time if initial velocity, initial position, acceleration, and elapsed time are known. Here, initial and final time may be arbitrary. For convenience, let u is the initial velocity and x0 is the initial position at time t equal to 0 and x is the final position at time t, then area enclosed by the VT graph and time axis is equal to the area of trapezium OACB dash, which is equal to half sum of OA and B dash C multiplied by OB dash. Since OA is equal to U, B dash C is equal to V and OB dash is equal to T, then the area enclosed is equal to, using the relation for velocity time, we can rewrite the relation as area is equal to x minus x0, which is further equal to ut plus half at square. We can further rewrite the relation as x equal to x0 plus ut plus half at square. This shows that the position of an object at any time t has quadratic dependence on time when the particle moves with uniform acceleration along a straight line. If s is the displacement of the particle in time t, then x minus x0 is equal to s, and the relation becomes s equal to ut plus half at square. This is the generalized expression for displacement as a function of time and helps us to determine the displacement at any time if initial velocity, acceleration, and elapsed time are known.
Let us try some numerical problems based on position-time relation. This is the velocity time graph of an object moving along a straight line. You have to calculate the distance covered by the object between first 5 seconds. मान लो S1 ओ दूरी है जो कि समा t बराबर है 0 तो t बराबर है 5 सेकंड विच तय की गई है ਤਾਂ S1 बराबर है ट्रेपेजियम OABB डैश ਦਾ ਖੇਤਰ जो कि बराबर है sum of AB and OB dash multiplied by AA dash ਦਾ half. S करके S1 बराबर है 3 जमा 5 गुणा B ਦਾ ਅੱਧਾ जो कि 80 मीटर है. Now calculate the distance covered by the object between the time interval between t equal to 0 to t equal to 10 seconds. Let S2 be the distance covered in the time interval between t equal to 0 to t equal to 10 seconds. Then S2 is equal to the area of the trapezium OABC, which is equal to half of the sum of AB and OC multiplied by AA dash. Therefore, S2 is equal to half of 3 plus 10 into 20, that is 130 meters. Let us try one more problem. A boat moves slowly inside a marina with a constant speed of 1.5 meter per second. As soon as it leaves the marina, it speeds up and accelerates at 2.4 meter per second square. You have to measure how fast is the boat moving after acceleration for 5 seconds and how far has the boat travelled in this time. First of all, let us draw a velocity time graph for the motion of boat. We know its initial velocity is 1.5 meter per second and up to next 5 seconds it accelerates with an acceleration of 2.4 meter per second square. Velocity time graph for these 5 seconds should be a straight line with a slope of 2.4. ਅਸੀਂ slope 2.4 ਦੇ ਨਾਲ ਇੱਕ ਸਿੱਧੀ ਰੇਖਾ ਖਿੱਚਦੇ ਹਾਂ ਜਦ ਕਿ B' ਬਰਾਬਰ ਹੈ U ਦੇ ਜੋ ਕਿ 1.5 ਮੀਟਰ ਪ੍ਰਤੀ ਸੈਕਿੰਡ ਹੈ। BB' ਬਰਾਬਰ ਹੈ V ਦੇ। ਇਸ ਕਰਕੇ BC ਨੂੰ AT ਦੇ ਬਰਾਬਰ ਹੋਣਾ ਚਾਹੀਦਾ ਹੈ ਅਤੇ AC ਬਰਾਬਰ ਹੈ 5 ਸੈਕਿੰਡ ਦੇ। ਇਸ ਲਈ BC ਨੂੰ 12.0 मीटर प्रति सेकंड के बराबर होना चाहिए है। फाइनल वेलोसिटी v बराबर है 1.5 अते 12.0 का जोड़ जो कि 13.5 मीटर प्रति सेकंड बनता है। तय कीती दूरी नूं मापण लई सानू रैक्टेंगल OACB डैश ਅਤੇ ट्रायंगल ABC ਦਾ ਏਰੀਆ ਮੈਜ਼ਰ ਕਰਨਾ ਹੋਏਗਾ ਜਿੱਥੇ ਕਿ ਏਰੀਆ ਆਫ ਦ ट्रायंगल ABC ਬਰਾਬਰ ਹੈ AC into BC ਦਾ ਅੱਧਾ ਅਤੇ ਇਹ 30 ਮੀਟਰ ਦੇ ਬਰਾਬਰ ਹੈ। ਏਰੀਆ ਆਫ ਦ ਰੈਕਟੈਂਗਲ ਇਜ਼ ਸਿੰਪਲੀ OA into AC ਅਤੇ ਇਹ 7.5 ਮੀਟਰ ਦੇ ਬਰਾਬਰ ਹੈ। ਇਸ ਤਰ੍ਹਾਂ कुल तय कीती दूरी दोनों क्षेत्रफल का जोड़ है जो कि 37.5 मीटर है। Let us now continue for the final equation of motion. For this, let me remind you the method to measure the position.
In this velocity time graphs, distance travelled during the time interval Ti to Tf is equal to the area of trapezium BC dash, which is equal to half sum of parallel side multiplied by the shortest distance between the two sides. Therefore, the shaded area is equal to half of the sum of BB dash and CC dash multiplied by B dash C dash. It is clear from the graph that BB dash is equal to VI, CC dash is equal to VF and B dash C dash is equal to TF minus TI. Therefore, area enclosed is equal to half of the sum of VI and VF and multiplied by TF minus Ti. On substituting the value of Tf minus Ti from the velocity time relation as Tf minus Ti is equal to Vf minus Vi divided by A, and by eliminating T we get the area enclosed or the change in position equal to xf minus xi which is equal to half of the sum of Vi and Vf multiplied by Vf minus Vi and divided by A, which is further equal to Vf square minus Vi square upon 2A. This gives Vf square minus Vi square equal to twice of A times Xf minus Xi. It further gives Vf square is equal to Vi square plus twice of A times Xf minus Xi. ਇਹ ਐਕਸਪ੍ਰੈਸ਼ਨ ਸਾਨੂੰ ਇਹ ਪਤਾ ਲਾਏ ਬਿਨਾ ਕਿ ਕਿੰਨਾ ਸਮਾਂ ਲੱਗਿਆ ਹੈ ਦੋ ਵੱਖ-ਵੱਖ ਪੋਜੀਸ਼ਨਸ ਤੇ ਵੈਲੋਸਿਟੀ ਨੂੰ ਰਿਲੇਟ ਕਰਨ 'ਚ ਸਹਾਇਤਾ ਕਰਦਾ ਹੈ। ਇਸ ਫੰਕਸ਼ਨ ਵਿੱਚ ਵੈਲੋਸਿਟੀ ਨੂੰ ਪੋਜੀਸ਼ਨ ਦੇ ਫੰਕਸ਼ਨ ਵਜੋਂ ਸ਼ੋ ਕਰਦੇ ਹਨ, ਇਸ ਕਰਕੇ ਇਸ ਨੂੰ ਵੈਲੋਸਿਟੀ ਪੋਜੀਸ਼ਨ ਰਿਲੇਸ਼ਨ ਵਜੋਂ ਜਾਣਿਆ ਜਾਂਦਾ ਹੈ। ਇਹ ਯੂਨੀਫਾਰਮ ਐਕਸਲਰੇਸ਼ਨ ਲਈ velocity ਨੂੰ measure ਕਰਨ ਦੀ equation of motion ਹੈ। Here initial and final time may be arbitrary. For convenience, let u is the initial velocity and x0 is the initial position at time t equal to 0 and x is the final position at time t, then area enclosed is equal to the area of trapezium OACB dash, which is equal to half sum of OA and B dash C multiplied by OB dash. Since OA is equal to U, B dash C equal to V and OB dash is equal to T, then the area enclosed is equal to half of U plus V into T. Using the relation for velocity time, we can rewrite the relation as area is equal to x minus x0, which is further equal to V square minus U square divided by twice A. We can rewrite the equation as V square equal to U square plus twice A times x minus x0. If S is the displacement of the particle, then the relation becomes V square equal to U square plus twice A times S. This is the general expression for displacement as a function of velocity and helps us to determine the velocity at any displacement if initial velocity, final velocity, and acceleration are known.
For better understanding, let us try to solve some numerical problems. A car accelerates uniformly from a speed of 36 kilometers per hour to a speed of 144 kilometers per hour in 10 seconds. Draw a velocity time graph and determine the distance covered by the car as well as the acceleration of the car. Here, initial velocity of the car is 10 meter per second and after 10 seconds, final velocity becomes 40 meter per second. Since the motion is uniform acceleration motion, the velocity time graph of the motion should be a straight line graph. For the measurement of distance, we have to measure the area enclosed by the velocity time curve and the time axis, which is equal to the area of the trapezium ABB dash A dash, which is equal to half sum of AA dash and BB dash multiplied by A dash B dash. Therefore, the distance covered by the car S is equal to half of 10 plus 40, multiplied by 10, that is 250 meters. For the measurement of acceleration, either we can find the slope of the line AB, or it is equal to v square minus u square upon twice of distance s, which gives acceleration A is equal to 40 square minus 10 square divided by 500, that is 3 meter per second square. ਮੈਨੂੰ ਪੂਰੀ ਉਮੀਦ ਹੈ ਕਿ ਤੁਹਾਨੂੰ ਗ੍ਰਾਫ ਦੀ ਸਹਾਇਤਾ ਨਾਲ ਇੰਪੋਰਟੈਂਸ ਆਫ ਗ੍ਰਾਫਿਕਲ ਰਿਪਰੈਜ਼ੈਂਟੇਸ਼ਨ ਆਫ ਡੇਟਾ ਅਤੇ ਦ ਡੈਰੀਵੇਸ਼ਨ ਆਫ ਇਕੁਏਸ਼ਨਸ ਆਫ ਮੋਸ਼ਨ ਬਾਰੇ ਪੂਰੀ ਤਰ੍ਹਾਂ ਸਪਸ਼ਟ ਹੋ ਗਿਆ ਹੈ। ਹੁਣ ਅੱਜ ਦੇ ਇਸ ਪਾਠ ਨੂੰ ਖਤਮ ਕਰਨ ਤੋਂ ਪਹਿਲਾਂ ਆਓ ਅੱਜ ਦੀ ਕਲਾਸ ਵਿੱਚ ਜੋ ਕੁਝ ਅਸੀਂ ਪੜ੍ਹਿਆ ਹੈ ਉਸ ਦਾ ਸਾਰ ਕਰ ਲਈਏ। ਇਕੁਏਸ਼ਨਸ ਆਫ ਮੋਸ਼ਨ ਦੀ ਵਰਤੋਂ ਸਾਡੇ ਹਰ ਰੋਜ਼ ਦੇ ਫਿਨੋਮੇਨਾ ਦੀ ਡਿਸਕ੍ਰਾਈਬ ਕਰਨ ਲਈ ਕੀਤੀ ਜਾ ਸਕਦੀ ਹੈ। ਅਸੀਂ ਗ੍ਰਾਫਿਕਲ ਮੈਥਡ ਦੀ ਸਹਾਇਤਾ ਨਾਲ ਕਾਂਸਟੈਂਟ ਐਕਸਲਰੇਸ਼ਨ ਤੇ ਮੂਵ ਕਰਨ ਵਾਲੇ ਪਾਰਟੀਕਲ ਦੇ ਮੋਸ਼ਨ ਨੂੰ ਡਿਸਕ੍ਰਾਈਬ ਕਰਦੀਆਂ ਇਕੁਏਸ਼ਨਸ ਡਿਰਾਈਵ ਕੀਤੀਆਂ ਹਨ। If we draw the velocity time graph, velocity at time t equal to 0 shows the initial velocity of the object, whereas velocity at any instant tells the instantaneous velocity of the object, and the slope of the curve between any two points gives us the average acceleration during that interval. For a uniform acceleration motion, velocity time graph would show a straight line graph. That is, velocity varies linearly with time. In this velocity time graph, slope of the line is equal to the tangent of the angle subtended by the velocity time line with the time axis, according to which Vf is equal to Vi plus A times Tf minus Ti. This is the expression for velocity as a function of time. Another property of Vt graph is the area enclosed by the Vt curve and the time axis gives us the distance traveled by the object. In this velocity time graph, distance traveled during the time interval Ti to Tf is equal to the area enclosed by the Vt curve and the time axis during the time interval from Ti to Tf. Therefore, the distance traveled or the change in position is equal to the area of trapezium BCC dash B dash, which is equal to xf minus xi, that is equal to Vi multiplied by Tf minus Ti plus half of A multiplied by the square of Tf minus Ti. This is the expression for position as a function of time. Final equation of motion is the relation between the velocity and position. This is Vf square equal to Vi square plus twice of A into xf minus xi. This expression allows us to relate the velocity at one position to the velocity at another position without knowing how much time is involved. ਇਸ ਤੋਂ ਪਹਿਲਾਂ ਕਿ ਅਸੀਂ ਅੱਜ ਦੇ ਇਸ ਪਾਠ ਨੂੰ ਸਮਾਪਤ ਕਰੀਏ, ਤੁਹਾਨੂੰ ਕੁਝ ਪ੍ਰਸ਼ਨ ਪੁੱਛਦੇ ਹਾਂ। My first question is, how will you determine the displacement with the help of a velocity time graph? The answer says it would be the area enclosed by the Vt curve and the time axis during the given time interval. The next question is, how will you determine the acceleration with the help of velocity time graph? The answer is, it would be the tangent of the angle subtended by the velocity time line with the time axis. I hope you enjoyed the lesson and must be looking forward to the next class. ਪਾਠ ਤੇ ਧਿਆਨ ਦੇਣ ਲਈ ਤੁਹਾਡਾ ਸਾਰਿਆਂ ਦਾ ਧੰਨਵਾਦ।